Okay, so our topic for today is exponential growth and decay. And here's the general formula for it. And we just want to go and take a look and see what each of these variables in our formula means. So this first amount is the final amount that we want to find. So whatever is growing or decaying, after our test takes place, what we're left with is this A, the final amount. C is the amount we start with, or the initial amount when we start our test, right? And now the plus and the minus sign we're putting in here because we've got a 1 in place there, and the plus sign basically means that if I make a number bigger than 1, that means that I'm going to have an exponential growth. Whatever I'm starting with, whatever C I'm starting with, if I see that plus sign in there, it means that that amount is going to be growing over time. Okay? And likewise, the negative sign is going to make this value in here less than 1. So that means that my C value is going to be going through exponential decay. So I'm going to end up with less of what I started with if I'm using the minus sign here. Okay? And R is the rate at which my original amount is growing or decaying. You got to be careful with this one because often it's given in the question as a percent, but you have to write this in as a number. Okay? So make sure that when you write the rate into the formula that it's a number and not a percentage. And finally, T is the amount of time I'm measuring the decay or the growth of my C. So there's our variables, right? So let's try an example here. Okay, and so the population of Johnson City has grown at a rate of 3.2% per year since 1990. If the population in 1900 was 25,000 people, what was the population in the year 2000? So let's go and define some of our variables here. We'll put the formula up here so we know what we're dealing with. Plus or minus r all to the t. Okay? And so it looks like here I've got a rate. So there's my r. And it's 3.2% or 0.032. Okay, we have to write it as a number. Okay? And the initial population that we're dealing with, our C, looks like it's going to be 25,000. Right? The amount of time that we're watching that population grow is in between 1990 and the year 2000. So that means that we're looking over a time of 10 years. And we're trying to find our A, which is the total population after 10 years. After 10 years. Okay. And the nice thing about the formula here is that it takes care of pretty much everything else for me. So I'm going to dump everything into its right place. So 25,000 is my C. This is an exponential growth question. Okay, because my population, I'm expecting it to grow. So I use the plus sign. I'll dump my number in, my rate in as a number, and the amount of time that it's growing for is 10 years. Okay. And after that, it's just an issue for the calculator. So let's see if I can get it here someplace where you can see what's going on. So I'm going to say that 25,000 times, you have to use the parentheses right here, 1 plus 0.032 all to the exponent of 10 gives me, and my population turns out to be 34,256. And they've got a 0.026 here, but because I'm measuring people, okay, it's a population, I'm going to, in my final answer, when I go to write the solution statement, I've got to make sure I round this to the nearest person. I can't have 0.026 of a person. So, in the year 2000, Johnson City will have 34,256 people. Okay? So that looks like a good one. Okay, let's try another one. So, this is a depreciation question. And depreciation means that the value of the item is actually decaying over time. So here we've got a vehicle. So you're not going to be able to sell your vehicle 5 years down the road for the same price that you bought it at, because its value is depreciating. And even though it's a depreciation question, I can still use the same formula. So here we go. So A is equal to C times 1 plus or minus R all to the T. Okay, so let's look at our pieces here. So a tractor has a depreciation rate of 19% per year. If the original price of the tractor was $29,000, what is the value of the tractor 5 years later? So my rate here, my R, is equal to 19% or 0.19. Divide that by 100, it gives me 0.19. Okay. My original cost of the tractor is, it's the biggest value for the tractor that we're going to have. It's $29,000. Okay, so the tractor is new at $29,000, and every year after it's going to depreciate by this 19%. Okay, and we want to know how much the tractor is worth after a time of 5 years. Okay, so let's dump those values into our formula here. So 29,000 times, and now because this is a depreciation question, I need to use the minus sign in here when I go and express this as my rate. This one really represents my original amount, and so I'm going to multiply by a factor here if it's depreciating by a number that's less than 1. Okay, so that's why I use the minus sign, depreciation. Right? The amount of time that we're going to measure this decay over is 5 years. So let's dump that into our calculator and see what we're left with here. So 29,000 times 1 minus 0.19 all to the exponent of 5 equals, and that all gives us a grand total of $10,111.67. I'm going to round to the nearest cent there. Okay, so to finish it off and to write my solution statement, my tractor, the tractor, will have a value of $10,111.67 after 5 years. Looks good. Okay. Okay, we'll do one more example here, and this is an investment question. Our tractor question shows us how I can lose money with exponential decay, and this is showing you how you can gain money with exponential growth. So suppose you invest $1,000 in an account paying 5.5% interest compounded annually. Find the balance after 3 years. This is a compound interest question, and Einstein called compound interest the most powerful force in the universe because of what it can make you, the type of money it can make you. And so let's do this in the calculator first here. I just want to show you what compound interest is. Okay? So what it means is that if I put my money in the bank for a certain amount of time, the bank's going to pay me interest for leaving it in there. They're going to use my money to do their thing with it, but for me allowing them to use my money and to keep it in there, they're going to pay me an interest rate for doing business with them. Okay? So how compound interest works is I'm going to put my $1,000 in, and after the first year, when it's still in there, they're going to give me 5.5% interest on it. Okay? So basically, they're going to give me $55 at the end of the year just because I left my money in with them. Okay? But my second year, I'm going to add that 55. That's the total that I have in my account, right? So I'm starting with, at that second year, $1,055. And now at the end of the second year, they're going to pay me again. But rather than that interest working on this interest rate, working on my initial amount that I put in, it's also going to collect interest on the interest of what's in there. Okay, so the same rate is going to apply. I'm going to multiply that by 0.055, but here I'm going to make a little more that year. I'm going to make $58.25, or $58 and around 3 cents. Okay, so finally in my third year, okay, so I'm going to add those two up. I'm going to add 1,055, which is what I had at the start of the second year, with 58.025, the interest at the end of the second year, and I'm starting my third year with $1,113.025. So finally, at the end of my third year, it's this amount that's going to get hit by that 0.05, the 5.5%. So multiply that by 0.055, that gives me $61.21. So if I add that to what I had at the start of the third year, okay, it's going to give me $1,174.24. Okay, so let's write that up in the corner here and see if our formula works for us. Okay, this is like the long way to do it, showing how that compound interest, I'm making interest on interest every time. First I had the $55, it increased to $58, and now I'm up to $61 for the interest that the bank is paying me. And I haven't entered any more money into the bank. Okay, so let's use our formula here. Okay, so my initial amount is going to be $1,000. My rate, okay, it's compound interest, so I know I'm growing here, so my rate is going to be 0.055, and that is going to happen, we want to figure out, for 3 years. Okay, so let's try that in the calculator here and see. 1,000 times 1.055 all to the exponent of 3 equals, and looky here, it's the exact same amount as we ended up, the same $1,174.24. Okay, so yeah, that's it. We're going to finish off our question by writing the solution statement out, that the balance is $1,174.24 after 3 years.